Hi there, this video is for chapter 3, sections 3.1 through 3.3. And the main learning objectives are we're going to be trying to find and explain different types of center measurements, different types of variation measurements, and different types of shape descriptions. Those three things are going to be important whenever we try to describe a distribution of data. The next important learning objective is to use the empirical rule to relate x values in a normal distribution with the percentage of data that's above or below or between those x values. It's okay if you don't know what the empirical rule is. That's part of today's lecture to try to explain that to you. Next, we're going to try to find the z-score, sometimes known as the z-value of an x value, and explain its significance. Next, we're going to relate x values in a distribution with the percentile. And lastly, we're going to find a 5-number summary of a data set and create a box plot, which is basically a visual representation of the 5-number summary of the data set. All right, well, let's get going here. By the way, chapter 3 is kind of the first chapter where we start doing some calculations and doing some math stuff, formulas and stuff. In the first chapters, we were doing a lot of vocabulary and a lot of explanation of kind of the idea behind statistics. And mind you, there's still plenty of vocabulary in chapter 3, but we are moving a little bit towards the mathy stuff. In 3 and 4, we'll do lots and lots of math. So if you were waiting, your time has come. All right, so the first learning objective here is to find and explain different types of center measurements. For our class, there's 3 main types of center measurements. These are things that try to find the center or the middle of a set of data. So they are called mean, median, and mode. The mean is sometimes called the average value. We tend not to use the word average in statistics because it can mean median or mode or other things. So we do use the word mean, M-E-A-N, when we're talking about this sort of average where you add all the things up and divide by how many there are. Like the average test score, you add all the test scores together, divide by how many tests there were, and that's your average test score. We're going to be talking about the sample mean and the population mean. And they come up quite a bit. So there's special symbols for the sample mean and the population mean, and they're right here. The sample mean is an X with a little bar over it. And the population mean, we always use this sort of curly U. It's called mu. It's one of the Greek letters of the alphabet. So we're going to use the mu symbol to represent the population mean. And then I have the formula here using the summation notation. We add up all the X numbers. That's all the data. Data is the X's. So add up all the X's, divide by how many there are. So that's the classic. You sum all the numbers together, sum all the X values together, and divide by how many there were. That's the mean. The median is the center or middle value. So what we mean by that is that half of the X values are larger than the median and half are smaller than the median. So it's sort of the middle point in terms of all the data, listed from low to high. It's the one in the middle. The mode is the most frequently occurring X value. Mode is not used very often and is certainly only used when there is a clear X value that occurs more frequently than others. So you will have some questions about the mode, which is just the most frequently occurring X value. Let's do some examples so we can see this, see these different kinds of center measurements in action. All right, so I just have an example here of some sample data, which represents employee compensation in thousands of dollars. So these are the X values. These are the employee compensation values, and they're measured in thousands. So we have one employee making $2,000, another employee making $3,000. Oh, another person making, so 2 people making 3,000, etc. So these are all the different data values. All right, so the sample mean, how do you find the sample mean? Well, you add everything up. So I'm going to be adding 2 plus 3 plus 3 plus 5 plus 5. I have to add all these things up. Okay. I'm just going to write it out. Just give me 1 sec. We really do have to add all these up. I do believe there are 13 of those. You should verify it. And so it's this giant thing. That's supposed to be a plus there. divided by 13 because there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 data items. So if you add all these numbers up and then divide by 13, you get the mean. And I did this before, and I wrote my answers over here just to kind of keep me on track to make sure that I'm not making too many blunders. So if you add this up, I do believe you get 260, and then divided by 20, divided by 13, which is equal to 20. So that's why our sample mean, our mean is 20, because we add up all the data points, divide by how many there were, and we get a total of 20. The median is where half of the values are higher and half the values are lower. There are 13 data values here. And so if there are an odd number of data values, this becomes a little easier to find for the median. For example, in this particular case, I'm going to find the seventh one. 1, 2, 3, 4, 5, 6, 7. Oops. 1, 2, 3, 4, 5, 6, 7. So the seventh one, why did I find the seventh one? Because that means 6 are lower. 1, 2, 3, 4, 5, 6. There's 6 guys that are lower than the 9, than that X value I chose to be the median. And of course, there's also 6 values. 1, 2, my pen. 1, 2, 3, 4, 5, 6. There are 6 values that are higher than that 9. So 9 is the number that splits sort of the data in half. Half are lower and half are higher. So we say the median is 9. That would be the measure of center median. Okay, for mode, we're looking for the thing that occurs most frequently. So 2 only occurs once, 3 occurs a couple of times, but many of you probably have already spotted the fact that 10 occurs 4 times. It's more than anything else. And so we're going to say the mode is equal to 10. It's the most frequently occurring number. Now, I do have a thing here at the bottom called outlier. That's not a measure of center. It's just something referring to the previous chapter, chapter 2, talked about potential outliers. They are values in the data, they're X values, that don't seem to be part of the rest of the data. Like there's a bunch of data, they're somewhere kind of related to each other, and then there's something which is way far apart, and it could be some strange anomaly. It could even be an error, but we typically want to identify potential outliers. We will have some formulas to help us identify outliers, but right now we're just going to kind of do it by intuitiveness, kind of looking at this. People will see 165 and say, gee, that's like a 3-digit number and 100 more than 150. And all these numbers are just like single digit or low 2-digit numbers. And so 165 seems to be like way, way out of the realm of the rest of the numbers. So 165 is definitely a potential outlier. Now, some of you keen-eyed people will say, well, 20 doesn't seem to be too close. I mean, there's like 2 to 10, which is most of the stuff. And 20 is like double the biggest value. It jumps from 10 to 20. So maybe 20 is a possible outlier. And that's a great way of thinking. So 20 is a possible outlier. I'm not going to try to dive into the whole isn't an outlier thing. I just want to keep us aware that there are potential outliers. And I'll give you an example of what happens when we identify and look at data with and without outliers, right? Because that's going to be important for us. So good thinking, 20 definitely could be an outlier. We'd have to do some calculations to see if it's considered mathematically an outlier, and we will do those in another chapter. All right, so those are the different measurements of center and examples for each of those. All right, so next page here, we're going to be talking about different types of variation. Variation is measuring how spread out the data is. Is it all bunched towards sort of, some middle value, or is it really spread out far away from the middle value? So the variation isn't really the middle, it's the spread of the data. We have 4 different main types of variation measurements in our, beginning statistics course, the course we're in. They're called standard deviation, variance, range, and IQR, which stands for interquartile range. So I'll briefly go over those 4 things, and then we'll do an example. It's actually the same data set. We'll do an example of finding those particular values. So for standard deviation, it's basically an average of how much the data is different from the mean. So we know that the mean from before, if you remember from the previous page, we calculated the mean, oops, to be 20. Did my writing not get in here? Let me fix this here. This was 100. This was 260 divided by 13, which is 20. I don't know what happened. Maybe I erased it by accident. Maybe I never wrote it. But the 20 was the mean of these. That's when you add them all up and divide by how many there are. So that's the middle in terms of an algebraic, average of scores. So these numbers, only one of them is 20. Most of them are, not 20. So we look at the difference between a number and 20. Like 2 to 20, the difference is 18. 3 to 20, the difference is 17. So we look at how much the data differs from that mean, and we average those together in a special formula. And the formula is down here. There is a formula for S and a formula for this little circle with a hat on top, which is called sigma. The reason why there's two formulas is because, once again, we oftentimes do standard deviations for samples and also standard deviations for populations. So whenever we do a sample standard deviation, we always use the letter S, lowercase s. And whenever we do a standard deviation for a population, we use a Greek letter that represents S, and it's pronounced sigma. It's like a circle with a little hat to the right. So those are the symbols that you'll need to recognize for sample standard deviation and population standard deviation. They're very similar formulas, but slightly different for each of those two calculations. So that's standard deviation. It's pretty complicated to calculate standard deviation by hand, because you literally have to find all the differences between 2 and 20 and 3 and 20 and 5 and 20. You end up squaring and adding them together and square rooting them. It's a whole big mess. So we typically don't do a lot of standard deviation calculations by hand. It's just very slow, tedious, and prone to making mistakes, because there's so many calculations that we have to do. It's just easy to make a little mistake somewhere. So I'm going to be showing you how to use StatCrunch to calculate a sample standard deviation. The second variation measurement that I'm going to talk about is called variance. Variance, it's very similar to standard deviation. And the symbols, you can see the sample variance is S squared as opposed to S, and the population variance is sigma squared as opposed to sigma. And in fact, if you're good at looking at formulas, you can see that the formula for S and for S squared are virtually the same, except one is missing the square root. And the reason why we use S squared and sigma squared and like that is because it's literally the square of the standard deviation. So if the sample variance, the sample variance is the square of the sample standard deviation. That's why it's S squared. And when you square a square root, the square root goes away. And so S squared is that whole average thing without the square root. It's used in different types of calculations. So you'll just have to be aware of this thing called the variance. And some formulas use the variance, S squared, and some formulas use standard deviation, which is just like S or sigma. All right, the next type of variation is called range. Range is pretty easy to find. You just look at the biggest value of X and the smallest value of X, and you subtract them. You're looking at how far you go from the smallest to the biggest. Subtracting is basically finding a distance. So from 2 all the way up to 165, if I just subtract those two numbers, 165 minus 2, I get 163, which is how far I go from 2 to 165, and 163 is what we call the range. It's just basically a distance between the very smallest and very largest of the X values. All right, lastly, I'm going to talk a little bit about IQR. IQR is a little bit, it requires a little bit more conversation. We can't do everything at once. So I'm going to give you a basic idea of IQR. And then later in this lecture, I'll explain a lot more of IQR and what these things are. But I'm just going to try to put things together in a logical way. And that means a little bit you're going to have to hold on to a deeper IQR explanation until we get to that point in the class. All right, it will be in this lecture, though. It'll be one of the later pages. So IQR interquartile range, it's basically the middle 50% of the data. So a lot of times data is kind of bunched in the middle. If you talk about like, I don't know, heights of adult women, maybe the average height of an adult woman in this country is like 5'2" or 5'3" or something like that. And there's a lot of people who are sort of around that range. I mean, they're obviously very, very tall people. They're women who are over 6 feet tall, 6.5 feet tall, etc. But they're not many of them. It's very few. And there are, much shorter women who are in 4 feet range. But again, it's not as many as there are clumped around the middle, which is so they're the 5'2" or 5'3" range. I don't know the actual numbers. I'm just making them up, but I think you get the idea. So a lot of data is bunched around the middle, and the middle 50% of the data is called the interquartile range. It kind of gives us an idea where most of the data is hanging out near the middle of our data set. The formula for IQR is Q3 minus Q1. And again, we don't really know what Q3 and Q1 is. They're called quartiles. So there are 4 quartiles. Basically, the data can be split up into 4 sections. And so you split the data up into 4 sections. You subtract the third quartile from the first quartile, and that is called the interquartile range. Again, more on that later. All right, so let's do some number crunching for these measures of variation. Again, the same example data set I used. And we're going to talk about these measurements right here. And certainly things like range, just subtracting 165 minus 2, finding the difference between the maximum and the minimum x values, that we can do by hand, 163. But these other measurements typically are much harder to do by hand, and we wouldn't want to do those. We're going to use technology. So I'm going to jump over to StatCrunch. This is the spreadsheet program that we use for our class. And I've typed in all the data right here under var1. I've actually typed in the data here, missing the 165, missing the potential outlier. And I'm going to use that a little bit later to explain some differences between things. But I'm going to use var1 right now because that's where all 13 of our data items are. You see it goes to row 13. So row 1 to row 13 are 13 items right there. So what I'm going to be doing is I'm going to be finding out statistics about this data. So I'm going to go to the statistics pull-down menu, and I'm going to try to summarize some statistics. Since the data is put in columns, it's a column of data going vertically, I'm going to do summary stats, and I'm going to do columns. So once again, stat, summary stats, columns. So I'm going to choose that. And there's a couple columns to choose amongst. I want the var1, so I have to choose that. It'll verify that I have chosen var1 here on the right. And then there's a whole bunch of things that I can choose here in terms of statistics I want to measure. So I definitely want to measure standard deviation. That's one of the things we want to measure. I also want to measure variance. I'm going to use the control key and click on variance, so then they both appear. And if you just click one at a time, then they all replace each other. So you'll have to like choose one, hold down the control key, and then it'll add to the next. We also have range, and we also have IQR. There's the Q1, Q3, by the way. IQR. Okay, so I want those 4 things, and I don't need anything else here, so I'm just going to say compute. And up comes a little pop-up menu right here. It says the standard deviation of this variable 1 is 43.8197. The variance is the square of that number. It's going to be very big because 43.8 whatever squared is 1,920. The range we already knew was 163, biggest minus smallest. And the IQR turns out to be 5. Again, I'll show you why that is later in this lecture. So we'll go back to our worksheet here. Again, I've typed in the answers ahead of time just to kind of make the lecture go a little more smoothly. So that's the standard deviation number, that's the variance number, the range number, and the IQR. Those are all different measures of variation for our data set. All right, and we're going to be relying on technology quite a bit in this course. All right, so what I'm going to do now is do the same kind of calculations, but I'm going to do them with the data missing our potential outlier. We had this big 165 number, whatever it was, right? That was like this way, way far away. I said it's a potential outlier. Let's do the same calculations of standard deviation, variance, range, and IQR with this set of data. There's only 12 items now because I threw away the 165. So quickly go back to StatCrunch. I'm just going to put this over here for a minute. Go to Stat, Summary Stats, Columns. I'm going to choose var3 because that's the column with the numbers that only go up to 20. There are 12 numbers. You can see the 12th row is that, and the 1 is the top row, so there's 12 numbers there. Again, I'm going to be measuring standard deviation, variance, range, IQR, and I'm going to throw in median because I have a little bonus question about median after those 4 measures of median is a measure of center. It's not a measure of variation, but I want to talk a little bit about that as well. So I'm going to throw that into my little readout. Hit compute, and we got a new pop-up window here. Standard deviation is 4 as opposed to 43, so it definitely changed a lot. So these are the new numbers. 24 is the variance. That's the square of 4.9. The range is 18. The IQR is 6. The median is 8.5, as it turns out. All right. So again, I've already typed those numbers over here on the side just to have them, handy and ready. So sample standard deviation, according to this formula that StatCrunch did all the numbers for us, is 4.9, etc. The range you can verify very quickly. 20 minus 2 is 18. IQR, not so easy to verify by hand. And I'll talk about the median in a second. Okay, so why did I do this again? Like basically the same kind of thing. What I want to show you is that if we compare, I'm going to move me over there. If we compare the standard deviation and the variance, we compare the different types of variation with and without the outlier, something very interesting may be, kind of recognized. So the sample standard deviation with the big number, with the 165, scroll down one more, was 43, and then without was 4. So it changed a lot, like a factor of 10 or something like that, when we got rid of this potential outlier. Same with the variance. The variance was 1920, and now it's 24. So I'm not so concerned about what the numbers are specifically, but they changed dramatically. The range changed dramatically, 163 with the big number, and only 18 leaving that big number out. But the key thing is the IQR did not change very much. The IQR before was 5, and the new IQR is 6. And this is why IQR is used quite often in statistics, is because it's stable, it's robust, it's called, right? It doesn't really get affected by one number, which might be an anomaly, might be an outlier. So IQR is very nice because it protects us against some mistakes that might be there by including an outlier that should not belong in the rest of the data set. So that just kind of give you a little view. We have different kinds of measures of variation, and some of them are used in different situations. All of them are affected by outliers except for IQR. Okay, and then the reason why I wanted to talk about the median, I had mentioned before when we talked about the median, which is the measure of center, that if there's an odd number of data points, it's pretty easy to find. When there were 13 data points, we got 6 and 6 on both sides, and then that middle one was the other one, the 13th, right? So 6 plus 6 is 12, and the middle one is 13. But here, if you do 6 and 6, 1, 2, 3, 4, 5, 6. Here's 6. Oops, I need a pen here. If you have 6 here, that's 1, 2, 3, 4, 5, 6, and you have 6 here, right? There's 12 data items altogether. If you do 6 and 6, there's nothing in the middle, right? You've used all the data points. There's no data point left to be the middle data point. So when there's an even number of data points, the way we find the median is you find the two numbers that basically are closest to the median, which is 8 and 9, right? Those are the numbers that would be right above and below the median, and you just average them together. So what's between 8 and 9? 8.5. So that's why we have the median 8.5. It's what we do when we have an even number of data points and we want to find the median. So 8.5, definitely half of the numbers are above 8.5, half of the numbers are below 8.5, even though 8.5 isn't itself an actual data value. That's okay when we're doing things like median. All right, let's keep going. So the next objective, the next learning objective we have is to explain the different types of shape descriptions. So for this class, we have three main types of shape descriptions. They're called normal, skewed, and uniform. So I'll describe them very briefly. I also have pictures of each one so you can kind of see what the shapes look like. Okay, so for normal distribution, it has this little curve down here that you can see. The curve is definitely symmetric, and we oftentimes call this bell-shaped. The bell-shaped curves here, this normal curve, it starts out with a small x value. Okay, so it doesn't start with necessarily a small x value. I mean, it does. What I really want to talk about is it starts off with a small frequency. And it goes up to like a higher frequency and down to a lower frequency. And one thing that a lot of students don't sort of read or recognize when they're first learning statistics is that even though we just draw this little mathematical curve, just like here, this is not really what's going on. What's going on is there is a histogram, like a bunch of like x values and their frequency. If you remember from the last chapter, from chapter 2, we found an x value and we put a bar which represent the frequency. And there's another x value here with a bar, and there's one down here. These are a bunch of bars, right? And each one has a particular frequency for that data value. So different data values have different frequencies, and you basically get a bunch of bars. And what they're graphing is just the tops of those bars. They're just kind of showing the tops because drawing the bars in is tedious and it's messy, right? Even though I drew my bars in there, it looks kind of a mess in there now. So they tend not to draw the bars very much. And you're supposed to know that this is just a histogram where the frequency of each x value is in the vertical. So they, I guess, really should have a vertical axis here and say frequency. Frequency. And this right here is the x values, or the variable, we call it. So horizontal is the x values, the variable values, and then the y, the vertical axis is called frequency. And you have a lot of frequency in the middle, so lots of stuff in the middle. And then when x's are small or large, like again, the height example I gave before, a lot of people kind of bunch towards the middle. And as you go to more extremes, taller and shorter, you get fewer people. So normal distribution is just another type of histogram where it's symmetric and it goes from low frequency to high frequency to low frequency. Okay, skewed is the next type of sort of shape that we want to be talking about. And there's two types of skewed, right skewed and left skewed. Right skewed means the data kind of extends more to the right, and left skewed means it extends more to the left. So this is an example of right skewed right here, because the data extends more to the right. And over here, this is left skewed because the data extends more to the left. One little interesting fact about right skewed and left skewed, as opposed to normal, for a normal distribution, because it's symmetric, the mean is going to be the same thing as the median. The average value, there's equal number of high numbers and low numbers. The average is right in the middle, and the median, by definition, is right in the middle. So, fun fact, for normal distributions, the mean and the median and even the mode will all be right in the middle. For a right skewed data set, for a right skewed distribution, because you have more numbers that trail to the right, you have bigger x values. So you have bigger x values. When you add up those bigger x values, divide by the number, you're going to get a bigger mean. So the mean of a right skewed data set is going to be larger than the median or the mode of a right tailed or skewed data set. So it basically moves to the right, you have bigger numbers, so therefore we're going to have a bigger mean. And likewise, we're going to have a smaller mean when you have smaller numbers that trail to the left. Let me see if I can fix that. Oop. So here the mean is going to be smaller than the median or mode in a left-tailed or left-skewed data set. All right, and the last common type of shape is called uniform. Here, I got a picture where they did draw on the bars. So these are all, these are the histogram bars. These are the frequencies. So for each X value, there's a frequency, and they're all right about that. They don't have to be exactly the same, but some are a little bit higher, some a little lower. But if they're all right about the same, we call that a uniform distribution. Uniform distributions come up a lot when we do probabilities or probability distributions, and that's chapter 4 when we're doing that kind of stuff. So that'll come up next chapter. When you're asked to describe a distribution in statistics, when you're asked to describe a distribution of a data set, what you're really being asked to do is give 3 things. You're asked to give the center, the variance, center, the variation, and the shape. So center, variation, and shape. The 3 things we just talked about, I'll go back up to the top if I can. You gonna work for me? There we go. So the center, the variation, and the shape, these 3 things right here is what you want to give. Someone says, what's the distribution? You're like, I don't know what that means. What it means is, what's the center number, what's the variation number, and what's the shape? So those are the 3 things we want to explain that tells us what we need to know about a distribution of data. All right, so our next learning objective here is to use the empirical rule. So I'm going to jump to that. I think that's this page. No. Is it? Yeah, here it is. Use the empirical rule to relate X values, that's the data values, in a normal distribution with percentage of data above, below, and between. So I have down here another normal distribution, has low frequency to high frequency to low frequency. And I have some other numbers kind of put in there to help us with what the empirical rule is. Okay, so once again, data bunched to the middle, and less frequent outside of the middle. So the empirical rule is also often known as the 68, 95, 99%, 99.7% rule for normal distributions. And those numbers seem quite random, and in a way they are, but they are numbers that come up so frequently that most students who finish statistics, even a year later, they remember 68, 95, 99.7 because it just comes up so often. So what do those numbers represent? Well, in a normal distribution, we have all the data bunched together in the middle. If you do one standard deviation, our standard deviation calculation, we can do on StatCrunch. If we do one standard deviation above and below the middle, that mean number, then 68% of the data are going to be there. So let me show you what that means. So here's our normal distribution. In this particular situation, we have a mean of 60. So the mean is the sort of value in the middle right here, measure of center, and has a standard deviation of 5. Standard deviation is a measure of how spread out the data is. And so if we go 5 this way plus 5, or 5 this way minus 5, we get 1 standard deviation. So this would be plus 1 standard deviation, and this would be minus 1 standard deviation. We oftentimes will label the x-axis using the standard deviation. So it's not random that we have 45, 50, 55, 60, 65, 70, 75 on there. That's because the standard deviation is 5. If the standard deviation were not 5, suppose the standard deviation were 10, we would typically do like 60, 70, 80, 90, and 50, 40, 30 going the other way. We would count by the standard deviation because it really helps us to see the shape and know how to use the graph, the normal distribution graph. So plus 5 and minus 5, plus 1 standard deviation, minus 1 standard deviation, that gives like a bunch of data in the middle, right? That's very high frequency X values. And in fact, the percentage of data, which is all in here, that percentage is 68%. So 68% of the data is bunched within 1 standard deviation plus or minus of the middle. And that 68% is more than 2/3. 2/3 is about 67%. So more than 2/3 of the data is within 1 standard deviation of the mean. And we can also do not just plus 1 standard deviation, but we can do another standard deviation. Suppose we go out another 5. So that would be 2 standard deviations, 2 plus 5s above the middle, or minus 2 5s below the middle, right? So that's plus 2 standard deviations or minus 2 standard deviations, because the standard deviation is just 5. So plus 2 5s or minus 2 5s gives us the range from 50 to 70. So 50 to 70, here's 50, here's 70. That didn't show up very well. Let me try blue. 50 to 70. This gives us a whole bunch of data here, more than 68%. In fact, that's the 95%. So the 68, 95, 99.7 is basically telling us how much data is kind of, within 1 or 2 or 3 standard deviations, how much data is in the middle of this distribution of X values. So for 2 standard deviations, plus 5, and minus 5, that whole range from 50 to 70 in this particular example will capture 95% of the data. And then the last number is going plus or minus 3 standard deviations. 3 standard deviations will get you to 45 and to 75. And that's virtually every single piece of data. 99.7% of the data is almost 100% of the data. Very, very little left over that we need to be worried about. So almost all the data is within 3 standard deviations of the mean of the center. All right, so let's do a couple calculations because this is our first, kind of calculation chapter. So my first question right here is, between what 2 test scores did the middle 68% of the class earn? This, by the way, is supposed to be like test scores of like grade school children, so, it's whatever context, doesn't really matter. It's a bunch of data that we have here. The way I was thinking of is like test scores. Okay, so between what 2 test scores did the middle 68% of the class earn? Well, the middle 68% is 34%, 34%. This is the middle 68%. And that's exactly 1 standard deviation above and 1 standard deviation below. That's part of our 68, 95, 99.7% rule. So between what 2 test scores? Between 55 and 65. That's the range of values, the range of X values, the range of test scores that captures the middle 68% of the data. All right, so a few more here. Below 60. So if we want to find below 60, we need to find out where 60 is. Well, 60 is right here in the middle. So we're looking to see what's below. We're looking at what percentage of the data is below 60. Well, 60 is right in the middle, and that means that half of the data is above and half of the data is below. So what percentage of the scores are below 60? That would be 50%. Because 60 is the dead on middle value, meaning there's half above and half below. What about between 50 and 70? 50 is over here. 70 is over here. Oops, get my pen back. 50 over here, 70 over here. That is between 2 standard deviations. Now you can add up these percentages. You can add 13.5 and 34 and 34 and 13.5, because this range right here contains all those percentages together. But just like we knew that 34 and 34 is 68, like the middle plus or minus 1 standard deviation is the 68 in the 68, 95, 99.7% rule. If I do plus or minus 2 standard deviations, which just says this is minus 2 standard deviations, and this is plus 2 standard deviations, that's exactly 95% of the data, because that's what the sort of empirical world tells us. So we know between 50 and 70 is 95% of the data. All right, let's do a little bit harder ones. So between 60 and 65, 60 and 65, here's 60, here's 65, 60, 65. So we're looking for just the data in between 60 and 65. Maybe that's not as hard as I thought it was, because it just says here 34%. That's half of the 68%. So 68% divided by 2 is 34%. That's the one standard deviation above, but not one below. It's half of the 68. So 34. And you can also see the 34 is written right there. So the image I decided to put on the lecture notes here kind of divides everything into little pieces to make it easier to help calculate stuff. All right, what about greater than 65? Okay, this is what I was thinking was maybe a little more challenging. So greater than 65. So here's 65. Greater than 65 would be all the stuff right here, all the stuff to the right. Now, sometimes people just like very quickly think, oh, all you have to add together is the 13.5 and the 2.35 to get the percentage above. And you would be very close to the right answer, but you wouldn't be exactly right because there's a little bit over here too. My pen, a little bit over here too. There's a little smidgen over there that you didn't add in. So it's going to be slightly more than 13.5 plus 2.35. How much? Not a lot more. You're not going to be off by much. So if you just want an approximation, just add those two numbers together. But I want to show you how to get the precise value because we will need those precise values. Okay, so how do we do this? Well, there's different ways of doing it. I'm going to show you one example. So, for example, we know that the data below 60 right here, this is 50%, right? There's 50% of the data going that way. There's 34% of the data in there, right? So all this is 50% and 34%. So all the stuff below 65 is 50% and 34%. This is the stuff below 65. So what's that going to be? 50, 84%. This is 50, 84%. So 84% is below 65. And if you remember, there's only 100%. All the data is 100% of the data. None of the data is 0% of the data. Half of the data is 50%. 100% is all the data. We know that there's 84% in this stuff over here. So the rest of it has to be up here, even this little smidgen. So if I take 100%, so the above 65, I would take the 100%, which is all the data, subtract off the 84%, and the answer is 16%. So the correct answer for greater than 65 is actually 16%. And that's slightly more than when you add 13.5 and 2.35. So there's an example. You can do it by subtracting, you can do it by adding. There's different ways of doing it, but there's an example of how you can find the percentage of the test scores that are greater than 65. All right. So I just want to remind you, feel free at any time to pause this video and try some of these problems. I have 3 more questions here, 5, 6, and 7. Why not give those a go? I mean, you may like, yeah, I'm getting the idea of this. Or you may just want to watch some more. So if you want to just watch some more, that's fine. But if you are able to challenge yourself and say, let me try to see if I can do these, and then compare my answers to what Jim gets, that's a much more powerful learning technique because as you go through this, you kind of have to remember and kind of enact the different steps to find these values. And you also will find out what you know and where you might get stuck. Where you get stuck, you're like, okay, I'm getting stuck right here. Let me watch the video to see how to get unstuck or what to do in the situation. And so it's a part of how you learn. You learn where you could get stuck and how to overcome that so that when it comes to like a test or something like that you're taking, you'll have that sort of experience of getting stuck and getting unstuck and what you have to do these types of problems. Anyway, just a recommendation to pause the video and try things, read things. That is a much more active way of learning and ends up being a much more powerful way that you tend to remember and be able to do better on with tests and things like that. All right, with all that little said, between 70 and 75, that's our next question here. Between 70 and 75, that's from here to here. Well, that's already labeled as 2.35%. You could also know that it's part of the 99.7%. So you could do 99.7% minus all these little values, and you would get 2.35%. All right, I'm going to erase some of this stuff just because it's kind of in the way. The next question is between 55 and 75. So between 55 and 75, again, that's not quite 3 standard deviations. So you can do the 3 standard deviations and subtract off a couple of values. For me, it might be easier if I just took all these internal percentages and add them together. 34% is this little part right here, or I guess this part right here. And then this part here is another 34%. And then this part is 13.5%. I got to make sure I line up my decimal places. And this is a 2.35%. So maybe I should be a better about writing my numbers here so people can kind of see what I do. So 34%, I'll put the percent over here, 34%, 13.5%, and 2.35%. When you're adding a bunch of decimals, you got to line up the decimal places. So there's only one number in the hundredths place. There's a 5 and a 3 in the tenths place. In the ones place, there's a 4, that's 8, 9, 10, 11, 12, 13. I'll put a little 1 up here. And then tens place, I get 1, 4, 7, 8. So 83, and my decimal place is right here. 83.85% of the data is between 55 and 75. And the last calculation here, the last practice problem for the empirical rule is below 70. Okay, so here's 70. We're looking for all this data below 70. And I think I'll do an adding version this time, right? I did a subtracting version before. So what I can do is I can find the data here. If I choose the halfway point, this data right here will be 50%. Half of the data is below 60 and half of the data is above 60. So we get a 50%. We already know the next two values. This value here is 34%. And this value here is 13.5%. So I can just add those all up, and that would be all the numbers that are below 70. Below 70, here's 70, and all the stuff is below. So I have to add up all these frequencies, all these percentages to find out all of the data below 70. So I got a 0.5 here. I got 0, 4, and 3 is 7. And I got 5 and 3 and 1 is 9. So 97.52% of the data is below 70. All right, so those are some examples of doing calculations with a normal distribution, talking about this empirical rule, 68, 95, 99.7% rule, which gives us an idea of where the data is located, sort of more in the middle, higher frequency in the middle and less frequency as you go further up. Okay, let's keep going. All right, so next item is related to what we just did. It's called the z-score. So math people have a z-score, or sometimes called a z-value, for every x value in a data set. So your data set's a bunch of numbers, a bunch of x values, and for each of those data values, we have a z-score for that x, for that data value. All right, and the z-score is exactly the number of standard deviations that x value is away from the mean. So a z-score is the number of standard deviations that the x value is away from the mean. So all we have to do is figure out how many standard deviations our x value is away from the middle, and that will be called our z-score. A z-score where the x value is larger than the mean will always be positive. So if I have my distribution, same picture as before, and I choose an x value that's larger than the mean, so 67 is an x value which is larger than the mean, then whatever z-score we get is going to be a positive, because if you're larger than the mean, the z-value will always be positive. Likewise, if you're below the mean, if you're at 50 or something like that, then the z-score will be negative. Negative values mean that you're smaller than the mean. And if the z-score is 0, that means you're right at the mean. You're not above, you're not below, you're exactly at the mean. So z value of 0, right here at 60, we would have a z value of 0. All right, there's also a nice little formula for calculating a z value that you should have in your notes somewhere, maybe on that page where you're having all your definitions and stuff. So the definition for the z-score is z is equal to x minus mu over sigma. What are these letters? Well, they're letters that I introduced today, so maybe you don't quite remember all of them. X is just your x value. Mu is the mean. It's the population mean. I'll put pop mean here. population mean, and sigma right here is the population standard deviation. So to find the z-score, you'll have to take your x value, subtract the population mean, and divide by the population standard deviation. So once again, this is the same problem I had before. So the mean of this data set, the mean of this population is 60. That's the middle value right here. And the standard deviation, equals standard deviation is equal to 5. We're counting by 5, so 1 standard deviation, 2 standard deviations, etc. So we're not the standard deviation isn't because we're counting by 5, just to remind you. Standard deviation was that crazy calculation with the square root and everything like that. I'll go back real briefly, maybe I can. Oops, not there. Is it here? Yeah, there it is. So this is the calculation formula. So you can do it by hand if you're really brave, but we use technology, typically put all that numbers in there, do all the crunching, and you get a number out. That's the standard deviation. So I just want to kind of mention this graph right here. It's not going by 5s because we feel like it. It's not going by 5s because that just kind of makes things easier. It's going by 5s because the big old, square root formula came up with the standard deviation of 5, right? So if the standard deviation were 7, we go from 60 to 67 to 74, whatever. We count by standard deviations, not just by whatever is convenient, right? Just to kind of make that clear. All right, so we're going to find z values of a bunch of numbers just to get some experience with finding z-scores. Okay, so what about for 65? Get rid of this stuff right here. I'll leave that there. Okay, so for 65, x is 65. Well, here's x equals 65 right here. That's 65. We want to know how many standard deviations above or below the middle is. Well, we know that the standard deviation is 5. Maybe I'll go up a little bit just to remind folks. Mean was 60, standard deviation is 5. So we're exactly 5 above the middle. So the z value would be positive 1. You can write 1, or you can write a little plus sign in there if you prefer. So 1 or plus 1 if you want. It's 1 standard deviation above the middle. In other words, the middle is 60, and 5 standard deviation, adding 5 one time, gets you to 65. So that's why the z-score is 65. And 55 is 1 standard deviation below the middle. So for the second problem here, for x equals 55, the z value would be negative 1. Because it's 1 standard deviation away, it's 5 away. Standard deviation is 5. So it's 5 away, but it's smaller. So it's going to be a negative as opposed to positive, which means that it's bigger. All right, so you might be able to have a guess at 70. 70 is going to be positive because it's bigger. And we do 2 standard deviations. We added 5 twice. So the answer for this one's going to be positive 2. 2 or plus 2 if you like. And I'm going to show you using this formula that the answer is 2. So here's the formula right here. Z, I'm going to do it in blue over here. Z is equal to the x value. For the x value for this problem, it's 70 minus mu. Mu is the population mean. The population mean we know is 60. So we're going to put a 60 up here. And then it's divided by the sigma, which is the population standard deviation. Once again, the standard deviation is 5. So our calculation for z will be x minus mu over sigma, 70 minus 60 over 5. 70 minus 60 is 10. And 10 divided by 5 is, in fact, 2. So if you don't want to think about like plus 5, I added 5 twice. So the standard deviation is 2. You can literally just put it into the formula and get the same result. So I brought that up also because for the next question, it says 67. So 67, I'm looking at this one right here, 67, is between 65 and 70. Like 67 is right around here. So we know that 1 standard deviation gets us to 65. We know 2 standard deviations gets us to 70. This is between 1 standard deviation and 2 standard deviations, like 1.5 standard deviations, something like that. I guess 67 is a little bit closer to 65, so maybe 1.4 standard deviations, something like that. It's going to be between 1 and 2 standard deviations, and we allow that. We allow decimal standard deviations. We're just saying it's part of the way to the next, right? So 1.5 would be halfway between 1 standard deviation and 2 standard deviations. but we don't have to estimate. We have a formula. So the z value, we take the x value, subtract off the mean, and divide by the standard deviation. So let's get the mean is 60, standard deviation is 5. So it's 67 minus 60 over 5. And that would be 67 minus 60 is 7 divided by 5. And 7 divided by 5 is 1.4. So we know that the value 67, the x value 67, has a z value of 1.4, which means it's 1.4 standard deviations above the mean. All right, one last calculation here. Okay, two last calculations here. For x equals 49, 49 is way over here. The reason why I'm using the graph and not just the formula is because we all are human. We all make mistakes. But I do know that this is going to be more than -2, like more negative, because it's below 50. So I know one standard deviation to the left is -1, another -1 standard deviation. So I've gone down -2 standard deviations and a little bit more. So it's a great way of just checking to make sure I'm not messing up somewhere. So I'll do my formula. I'll do select z is equal to x value minus the mu, the middle value, divided by the sigma, the variation value. And 49 minus 60, if you remember your numbering, you go to the whatever fair with $49. I don't know why I said fair. You go to the store with $49. Something costs $60. You don't have enough money. You're going to have to borrow. How much do you not have, right? You're going to have a negative. That's what negatives are. It's like what you're missing, right? So this is going to be a negative. From 49 from 60 is $11. So you're missing 11. All that's to say is 49 minus 60 is -11, right? So if you remember those negative number or calculation problems. So 49 minus 60 is -11 divided by 5. This works out to be -2.2. So the z value of x equals 49 is -2.2. I have z over here and 2.2 over here, but I mean, you would basically write them together. Z is equal to -2.2, right? So not spread out, but you say that's the answer for x equals 49. All right, and lastly, for x equals 80, x equals 80 is off the chart. Like 75 is already 3 standard deviations. 80 is like off the screen, like 80 is somewhere around here. And remember, like virtually all the data is within 3 standard deviations. So this has got to be way outside the 3 standard deviations. And it might even be 4, because remember, we're counting by 5s. I think it should be 4. Let's test it out. Z is equal to x minus mu over sigma. 80 minus 60 is 20. 20 divided by 5 is 4. So indeed, x equals 80 has a z value of 4, which is 4 standard deviations above the mean, which is basically at a frequency almost of 0, right? So the frequency of that x value is very, very small, because we're even outside the 99.7% of the data that lies between -3 and +3 standard deviations. All right, so those are some examples of the empirical rule, of the z-score values, with the idea of the empirical rule helping us guide us into what the answers should be. So I'm using the empirical rule to help me kind of gauge what the answer should be as a checking to make sure I'm not making mistakes. But these are called z-scores, right? We're doing the z-score of every x value, and that's the number of standard deviations from the mean. All right, we only got a couple of topics left. So obviously you're pausing the video when you need to, but if you're ready, we're going to do the next one, which is called percentiles. All right, percentiles are used both with non-normal distributions and also with normal distributions. That 68, 95, 99.7% rule only works for normal distributions. If you have a skewed distribution, and work no more, right? So, or if you have a uniform distribution, it doesn't work anymore. So for non-normal distributions, we can use percentiles. It's kind of why they're there, right? So we can work with them. However, percentiles are not completely always the same depending on what textbook you use. Generally, a percentile is just the percentage of x values, the percentage of x values that are smaller than it. So a percentile is the percentage of x values that are smaller than it. So whatever x value is, you find out how many are smaller, write that as a percent, and then you're good to go. That's the percentile. In our textbook, it kind of acknowledges this. On page 124 of the textbook, it says that other kinds of sources, even like StatCrunch, which we're using with our textbook, can get slightly different answers from textbook to textbook or from spreadsheet program to spreadsheet program. And it says specifically there's not a universal agreement on a single procedure for calculating percentiles, but we'll describe some relatively simple procedures of how to find them. And I include this little note down here. If there's ever a discrepancy between what the StatCrunch answer is and what the textbook formula is, I'm going to give you full credit for either answer. So you don't have to worry about which answer is more correct. You're going to get full credit for either answer if you're using the StatCrunch formula or if you're using the textbook formula. They almost always get the same results. So it's not like it's going to be different every time. But in the weird situations where they give different answers, you get full credit for either one. I did actually get an example here. I made this example so that it does have a discrepancy just to show you an example. But it doesn't come up as often as I'm sort of cherry picking the numbers to make it come up. So, okay. So for this one right here, again, the formula for a percentile, which is called PX, this is just the way they write it, is the number of X values divided by the number of X values that are smaller than X divided by the total number of X values. That gives you the portion or the fraction of X values that are smaller. And then we multiply by 100 because that's how we convert a fraction into a percentage, or a decimal into percentage, also multiply by 100. So multiply by 100 just converts those partial fractions, partial decimals into percentages. So that's a very simple formula. So let's do that. This is an example. Let's find the percentile of X equals 9. So here's X equals 9. We have to count the number of data values that are smaller. So 1, 2, 3, 4, 5, 6. There are 6 data values that are smaller. So the number of X values that are smaller is 6. And then we divide that by the total, if I can spell, number of X values. And you may remember this is the same data set I'm using for this lecture. There's 13 data set values there. So 6 divided by 13 is the number of X values that are smaller than 9, and divided by the total number of X values. 6 divided by 13, I can use like any kind of calculating program. So for example, I can use Desmos. Oops, back over here maybe. So 6 divided by 13, you got to multiply by 100 to make it into percent. So 6 divided by 13 times 100 gives us 46%, 46.15%. So 46.15% of the data, that's the percentile, 46th percentile. A lot of times you round it to the nearest whole number. So 46.15 or 46th percentile is where that number, the X value of 9 lies. So percentile 9 is 6 over 13. We're going to multiply it by 100, and we get 43rd percentile. So that's simple calculation of how to get percentile. I'll show you one more percentile of X equals 5. The reason I'm showing you this one is because there's more than one 5. So a little bit of ambiguity what we count here. But we have to count the number of values lower than the X value. So the X value of 5 occurs, of course, twice, but how many values are lower than 5? There are 1, 2, 3 values that are lower than 5. So our top number would be 3. There are 3 values literally lower than all the 5s. And there's 13 total values, and I multiply by 100. And if you do the calculation, was it 43rd percentile? Did I make a mistake? I don't remember 43. Let me go back and look at this. Oops. Different page. 46th percentile. So some of you are like, why is he putting 43 there? I thought it was 46. Yeah, you're right. It was 46. Okay. So, old people, they make mistakes. I guess everyone makes mistakes, right? So maybe I just blame myself more. But I did make a mistake. It is 46th percentile. 46th percentile. Because that's what the calculation was, even though I wrote it wrong. So apologies. So 3 over 13 times 100 ends up being the 23rd percentile. I won't do the calculation because I'll probably make a mistake anyway. But I do know it's half as much as 46. So it's 23rd percentile. All right, and then we're going to find the cutoff for the 80th percentile. So for the 80th percentile, I'll show you how to do using StatCrunch. So you see a little bit of StatCrunch in there too. So this is the data set going from 2 to 165, and we're looking for the 80th percentile. So let me go over to StatCrunch. I'm going to hide these guys. Doop, doop. They're not gone. See the little 2 up there? It just says that there's 2 hidden results, so you can get them back anytime you want, or you can delete them if you want to get rid of them. But I'm going to be looking at the percentiles for var1. So once again, I go to stat. I'm looking for a statistic like percentile. I'm going to look for summary statistics. My data is in a column. So once again, the same steps. I could choose var1. I'm not choosing var3 because that's the one that throws out the 165. So I got to choose my var1. It verifies there. And then it's not actually in this part right here. It's right below it. It says percentiles. So you write whatever percentile you want here. I want the 80th percentile. So 80. I want the 80th percentile. And then I hit compute. And a little pop-up menu will come. Oh, I guess it gave me all the other stuff too because I forgot to erase it. So I'm going to go here to edit. It gave me all these things here, right? So let me just do n, for example. That'll get rid of all that mess. All right, so here's my much smaller thing. So for var1, there's 13 data items, and the 80th percentile has the number 10. So the 80th percentile, this is an x value of 10. 80% of the data is supposedly smaller than 10. All right, so let me go back to my worksheet and come back. There we go, 80th percentile. 80th percentile is 80th percentile is x equals 10. Okay, let's make that look like an x and not some weird symbol. X equals 10. What's the cutoff for the 80th percentile? It's 10. Okie dokie. We are in the home stretch of our learning objectives for chapter 3. All right, we're at the last learning objective, which is the 5-number summary, and a box plot, which is a visual graph of the 5-number summary. And this is also where we're talking about Q1 and Q3, by the way. All right, so the 5-number summary is literally 5 numbers, right? And they're listed precisely in this order, and they're precisely these numbers. So the 5-number summary is the minimum X value, the Q1, the Q2, the Q3 value, and the X max value. These are all just numbers. So you're going to calculate 5 numbers, you're going to write them down, and that's called the 5-number summary. By the way, Q2, the second quartile, is also called the median. So some people write the 5-number summary as X min, Q1, median, Q3, X max, because the median is the same as Q2. So the Q1, the first quartile and the third quartile, it's where basically 25% of the data is and 75% of the data. So they divide the data into 4 portions, and the quartiles are where 25% and 75% of the data lie. So that's what they are. We're again going to be using StatCrunch to do those calculations for us because they're a little bit messy by hand. X min, by the way, is just the minimum X value. So I know the minimum value right here, the minimum X value right here is 2. So X min is 2. This should say X max. Typo. It's like a copy and paste error, right? This should say X max. Right, the 5-number summary is X min, Q1, Q2, Q3, X max. So X max is just the maximum value, which is 165. We know the median because we found it in our calculations before. It was 9. But we're going to be using a StatCrunch to get all these numbers anyway. So let me go over to StatCrunch. I'm going to go back to, get rid of this guy, go back to my summary stats, columns, var1, and all in this thing, we're going to be measuring the 5-number summary. So the 5-number summary starts with the minimum. That's the X minimum value. The next one is called Q1. So I'm going to hold down the control button and hit Q1. Q3 is there, but I'm going to put them in order because the order, math people get really picky about stuff. They really want the order to be the right order. So min, Q1, Q2, Q3, max. So I'm going to put Q2 next. The StatCrunch writes Q2 as median. So there's our Q2, our median. Then there's our Q3, and then there's our max. So 1, 2, 3, 4, 5 numbers. Min, Q1, Q2 median, Q3 max. Compute. Boom, here's the answers. So a minimum 2, Q1 is 5, median is 9, Q3 is 10, max is 165. I think we already got the 2, 9, and 165. Q1 is 5, Q3 is 10. Q1 is 5, Q3 is 10. And if you didn't notice, I actually put the answers down here just to kind of keep me on track. So I don't make too many mistakes in the lectures. So that's the five. So literally, that's the 5-number summary. The 5-number summary, you would write out those 5 numbers with commas. You said if someone asks you what the 5-number summary is, you say, okay, it's 2, 5, 9, 10, 165. You literally just list out the 5 numbers and say, there's your 5-number summary. The IQR, which we talked about towards the beginning of today's lecture, was Q3 minus Q1. So that's the formula for IQR, the interquartile range. It's Q3 minus Q1. Now we know what Q3 is. We know what Q1 is. It's 10 minus 5. So the IQR is 5. It's the distance or the subtraction between Q3 and Q1. Now we know that within 5 of x values of the middle, basically between these 5 x values, we get 50% of the data. So those 5 x values contain the median. So the median is 9. And we're going from 5 to 10. So between 5 and 10, between those two 5 numbers, between those two x values, those 5 numbers in between, 5, 6, 7, 8, 9, 10, right, we get 50% of the data. That's what the IQR tells us. So I wrote that actually right here. So 50% of the data lies between x equals 5 and x equals 10. Distance of 5, yeah. Okay. So our last bit, trust me, we're almost done. We got just a couple little graphs here, is what's called a box plot. Box plot is just a visual representation of the 5-number summary. So we take the 5-number summary and we do a box plot. All right, we can do box plots on StatCrunch. So to do a box plot, it's a graph. And there it is, box plot right in there. So I go to graph and box plot. And I want var1. I'm not going to use fences. I'm going to get rid of that because the whole outlier thing is kind of early for us. I'm going to hit compute, and it's going to give a vertical box plot. And I can also turn it around sideways. I could say draw boxes horizontally, which is what I did for our lecture notes. So that's what it is. I also just kind of stretched it out a little bit because it looks very smushy there. So I kind of like took this and I kind of bend it out like that. So there's the 5 numbers. The low is the minimum. Here's our Q1 and our median, or Q2 is right here. And you notice it kind of pops up with the numbers to kind of guide us right there. There's Q3 and there's our maximum over here, right? So that's what the visual representation called box plot of that is. So back over here, that's just basically a copy paste of that StatCrunch graph. So I'll zoom in just a little bit here. So that's what a box plot is. It's just a visual representation of those 5 numbers. Now, it is considered very good manners to put the numbers of the box plot in there. So what are the numbers? Well, that's just the 5-number summary numbers, right? The numbers are 2, 5, 9, 10, and 165. So we would literally write like 2, 5, 9, 10, and then, oops, I don't have enough space here, 165. You don't have to do this. If you don't write the numbers in on like a test, I'm still going to give you credit for it. But honestly, that's just kind of very good manners so that your reader doesn't have to like search, what are those 5 numbers I'm supposed to be saying, right? You force the reader to do all this extra work to try to figure out what the numbers are if you don't put them on the graph. By the way, this blue part right here, this blue shaded region, tells you where the IQR is. That's the middle 50% of the data. It's between 5 and 10. So they shade it in like that to sort of make your eyes go to where the IQR is. And lastly, I'm going to show you another box plot with the same data set, but just missing the potential outlier. So I'm getting rid of the 165, right? So I have the same data set. There's only 12 data. It's a smaller data set. There's only 12 items instead of 13 items because I threw away the 165. We can find the 5-number summary in the exact same way. You go to StatCrunch. You go to, I'll get rid of this thing for a while. you go to summary stats, columns, right? And then you select var3, and you again do the minimum, and then the Q1, the median, and then the Q3. So I didn't hold on I forgot to hold on the control key, so it erased it. Sorry. Minimum, Q1, median, which is Q2, Q3, and maximum. Okay, there we go. And it pops up with those 5 numbers. So it's the same thing as before. If you got the idea of how to find those calculations, it didn't change. I just showed people again in case they need a reminder visually of what it does. So as I did, I wrote down the numbers before. There's our 8.5, our median that we found before, because it's only an even number of data points. So 2, 4, 8.5, 10, and 20 are our 5-number summary. That's our min, Q1, median, Q3, and maximum. And the box plot, make the same way as I did before, choosing box plot. And this box plot is much nicer than the previous one. Again, good manners will tell you to label your box plot. So I write 2 here as my minimum value. 4 is here. 8.5 is the median. 10 is the Q3, and 20 is here. And again, this shows us the IQR, shows us that middle 50%. And so without our big outlier, without our 165, we get a much nicer looking graph that's like really clearly 4 to 10. Before, even when I stretched it out, we had like everything smooshed in here, like because it's so big here, we get all this space right here, and then all the rest of the data is like all right here. So anyway, so there's some visual representations of the 5-number summary, aka a box plot. So box plots you'll be doing in the chapter 3 homework and such. All right, well, that is all of the different learning objectives for, the major learning objectives for chapter 3. Just to reiterate, we wanted to find and explain the different types of center measurements, variation measurements, and shape descriptions. Those are the 3 main things we talk about when we talk about a distribution of data. We use the empirical rule, the 68, 95, 99.7% rule, to relate X values in a normal distribution with the percentage of data either above, below, or between those X values. We found z-scores, also known as z-values of an X value. So each X value had a z-value. We explained that the z-value was the number of standard deviations away from the mean. We related X values in a distribution with the percentile, the percentage of X values that are lower than a given X value. And we did the 5-number summary, 5 numbers that were particularly useful for us. You'll see more reasons in chapter 5. And we created a box plot, which is a visual representation, aka a graph of the 5-number summary. Hopefully this video was helpful to you. And if you have any questions, any what ifs, anything that you would like help with, please don't hesitate to reach out via email, stop by my tutoring hours, whatever. I hope you have an enjoyable day, and I hope I talk to you sometime soon. Okay. Bye.